In modern armored warfare, kinetic energy penetrators rewrote the rules, forcing tank armor to evolve from thick steel.
As we view these deconstructed panels, our focus is drawn to the concepts and design impacts that shaped history, not the mechanics of their construction. Concentrating energy into a small cross-section increases penetration potential.
Early armor was mainly thickness versus caliber.
This is the long rod penetrator. Slender, dense projectiles optimized for high-speed impact, a significant evolution over previous designs.
Sabot allows a smaller penetrator to be launched from a larger bore. As the carrier separates in midair, the penetrator continues its trajectory unimpeded. As penetrators improved, armor had to do more than just be thicker. Modern tanks utilize mass, slope, and layered defenses.
Sloping geometry significantly increases the effective path length through the armor, as demonstrated by how the water sheets off these angled plates.
For kinetic threats, angle also changes impact behavior and stress distribution. This is spaced armor. It forces a penetrator to interact with multiple interfaces, maximizing energy dissipation.
The rise of composites highlights combining materials to disrupt penetration mechanics.
Composites can be tuned for different threat types and impact angles.
Long rod impacts create intense, localized pressure and material flow at the interface.
To withstand extreme force, armor arrays utilize both hard external layers to deflect impact and resilient internal ballisting. We introduce the concept of non-homogeneous design, armor that behaves differently across depth. As we move through this mock-up,
Modern tank silhouettes changed. Thicker frontal arcs, different turret shapes, modular cheeks.
the frontal cone philosophy dictates that we protect the likely direction of threat approach most heavily.
Shifting focus to the turret design, the cheeks and mantlet regions emerged as critical design problems requiring immediate attention.
We introduce the weak spot challenge. These are the critical areas: openings for optics, crew access, and gun movement.
Designers distribute protection. Not everything can be maximum thickness due to weight.
This increased protection comes at a cost. The heavier the armor, the greater the stress on engines, suspension, and logistics.
Upgrade paths without redesigning the entire hull.
The modular design allows us to rapidly reconfigure these platforms, swapping protection packages to match diverse missions and evolving threat environments.
Progress in metallurgy means stronger steels and improved manufacturing consistency.
Penetrator evolution pushed armor beyond just steel into carefully engineered arrays. Across decades, armor design repeatedly returned to three core principles: spaced, angled, and layered protection. Non-explosive reactive approaches utilize dynamic layers designed to disrupt incoming penetrators before they reach the primary armor. Armor is now a system, combining base armor, exterior add-ons, and internal spall management layers. Fragments inside the vehicle can be as dangerous as penetration itself.
Interior liners and compartmentalization represent critical survivability responses. This mock-up demonstrates the
balancing protection across all arcs is critical. The system analyzes the distinct threat profiles for the front, sides, roof, and rear engagement zones.
Top attack considerations are high-level threats in modern battlefields. Therefore, roof protection is becoming increasingly relevant.
Kinetic threats remain central because they are fast, hard to stop, and purely energy-driven. This is the heart of armor development.
Exact armor arrays are sensitive, but design principles are broadly understood.
Crews rely on the strongest arc facing the threat.
We take the lessons learned on the battlefield and apply them directly to the next generation of armor upgrades. Penetrators keep improving, and armor answers with smarter structure. Steel, and it composite, and it modular, and it active.
The real story is the duel of engineering.
Active protection systems intercept and disrupt incoming threats before they ever hit the armor, creating a protective bubble around the vehicle.
Active systems change design priorities. Armor can be redistributed, but the passive layer must still survive failures. Modern survivability is multiple lines of defense.
More protection can reduce strategic mobility and increase fuel demand.
Modularity as strategy means we can upgrade armor systems without having to replace entire fleets.
This turret bustle design emphasizes internal safety philosophy. We isolate hazards like ammunition storage to protect the crew space conceptually.
Armor design emphasizes repairability. Damaged modules can be swapped faster than welded rebuilds.
When the threat mix problem means tanks must survive kinetic and shape charge threats, plus mines and drones. Optimizing for one threat can open vulnerabilities to another. Design is compromise. Balancing protection and mobility has always been key, but the rapid evolution of ammunition technology forced constant adaptation. First, digital models predict complex interactions with pinpoint accuracy. Then, these simulations are validated safely on the physical testing ranges.
Array tuning is the concept of changing layer order and geometry to reduce penetrator effectiveness.
The concept of yaw and deviation generally forces the penetrator away from its ideal path. These visualizations highlight the critical role of air gaps and interface effects in modern armor design.
Battlefield survivability relies on layered defense. As you can see, even partial disruption is enough to prevent catastrophic penetration.
Armor design must consider multi-hit resilience and damage tolerance. The plates are engineered to absorb successive high-velocity impacts without catastrophic failure.
The larger the protected arc, the heavier the vehicle becomes, until it is simply too heavy.
Side armor rapidly evolved, utilizing add-on skirts and reactive modules specifically designed to defeat modern threats on the flanks.
Enhanced underbelly survivability is a hallmark of this modern design, featuring advanced blast management systems proven effective over the harshest rocky terrain.
The future direction of defense is here. We are integrating passive armor directly with smart sensors and rapid countermeasures.
Why kinetic penetrators remain difficult? Short engagement times and extreme impact conditions.
Protection is also doctrine, presenting the strongest face to the threat, using terrain, and minimizing exposure.
Survivability relies on getting the right armor arc facing the threat quickly. This highlights the importance of rapid turret slew rates and effective stabilization systems.
Signature and survivability. Avoiding detection can reduce hits, complementing armor.
Heavy armor must remain serviceable in the field, requiring constant repair and sustainment operations.
Our upgrade ecosystem ensures that armor packages can be tailored precisely to the user's needs and budget constraints.
Penetrators focus on concentrated energy. Armor, however, focuses on disruption and survivability. Exact performance specifications are often classified due to security protocols. Therefore, our focus remains strictly on the visible design principles and technological trends.
The future armor stack features smarter sensors, lighter materials, and modular architectures.
Modern survivability is layered decision-making. Avoid, disrupt, absorb, and protect.
Kinetic penetrators forced tank armor to become a science of interfaces.
Visible design cues like the bulky turret cheeks, reinforced glacis, and modular blocks highlight the kinetic era's influence on this design.
Protection also impacts vehicle silhouette and crew ergonomics. Space is needed for layers.
As threats diversify, tanks rely on combined arms and situational awareness, not armor alone. Penetrators drove armor to become layered engineering under severe constraints.
Early steel tanks gave way to angled armor, then composite arrays, modular upgrades, and finally active systems.
The armor versus penetrator contest is a design dialogue across generations. This presentation is offered strictly as educational engineering history, not a guide to the construction of weapons.
Every improvement in the kinetic dart forced armor to stop thinking like a wall and start thinking like a system that can disrupt, absorb. Kinetic energy penetrators didn't just change ammunition, they reshaped tank design itself, pushing armor into layered